Section 4 is called Applications of Linear Systems. All this means is, in this section, you got story problems. They don't go away. You can't avoid them forever. If you do, well, your grade is just going to severely suffer. So this entire section is about certain types of story problems. We have three ways to solve all of our systems of equations at this point: graphing, substitution, and elimination. As you've probably noticed from the problems you've done, from the practice problems we've done in class or on the homework, sometimes one way of solving is better than others. Sometimes elimination is better than substitution. Usually elimination and substitution are better than graphing. So, when do you use those systems? If the directions don't specifically say to use substitution or elimination or graphing, then you can use whatever method you want. So when should you use each of those methods? And that's what this table right here is trying to tell you. For graphing, you want to use graphing when you want a visual display of the equations. If you really specifically want to see the graphs, then you would graph it. Or when you want to estimate. And I've talked about that before. Graphing really is just an estimation of solutions, because when you graph, you really can't get that accurate. And a lot of times the graphs of your lines won't even cross at like a nice grid point. So then you're just guessing anyway. So if an estimate is okay, then you can graph it. Substitution method, you should use that one when one equation is already solved for a variable. You got two equations and one of them says like x equals something. That's a good time to use substitution. Or when it's easy to solve for a variable. So like you got like 2x plus y equals 5, you could easily solve that equation for the y and then be able to use substitution that way. That's a good time to use substitution. Elimination is the one that you want to use basically when substitution looks like it's going to be ugly. Or when the coefficients of one variable are opposites already. Or when it's not convenient to use graphing or substitution. Okay? If you don't have opposites, you can make opposites pretty quickly. So if your equations, I would actually add to this, if your equations are in standard form, if you're in standard form, usually elimination is going to be the best, unless you have a variable that is easy to solve for. And then in that case, you might choose to use substitution. So, in this section, you're going to get story problem practice. You're going to have to read the problem, define your variables, write your system of equations, and then solve the system of equations using whatever method seems to be the best option. Here we go. So for this first problem, it says systems of equations are used to solve problems involving mixtures, rates, break-even points. Break-even points are kind of an important one. That's where companies or people make something and it costs them money. And they want to know how much they have to sell to break even, meaning so that they're not losing money anymore and they start making money again. Okay? They're recouping their cost of producing whatever it is that they produce. So where you start to make money instead of losing money. Businesses, of course, are interested in making money, so that's why they care about break-even points. So this is very relevant to you guys. In your jobs in the future, you may need to be running a business. You might be a manager or an owner of a business, and you need to know when you're going to start making money again. So, first of all, business. A fashion designer makes and sells hats. They must be great hats. The material for each hat costs $5.50. The hats sell for $12.50 each. The designer spends $1,400 on advertising. How many hats must be sold to break even? So what are the two things that are going on in this problem? The first thing we need to do is define variables. So we need to figure out what things are changing here. Hats sold, yeah. It says how many hats, right? So number of hats sold. It's not number of hats made, because I can make a bunch of hats. It's number of hats sold. What's the other thing that's changing? So you have the right idea. It's not really cost of material. It's not really how much money I've made. It's just money in general. So amount of money. Those are the two things that are changing. How much money I spend or make, and how many hats I sell. Okay, so we need two variables here. X and Y. And I'm going to call Y the amount of money. Because in this case, unlike the other problems that we've been dealing with recently, in this case we do have a dependent and independent variable. The hats sold dictates how much money I have. Okay? So that's why I'm calling that one X, and then the amount of money I'm calling Y. Now in these problems, you have to form two different types of equations than we normally do. Normally we write an equation that is like number plus number equals number, money plus money equals money. Well, that's not what's going on here. If you are working with a break-even problem, then you're going to have two equations, and your two equations are going to be a total profit equation and a total cost equation. Things that cost you money go in the cost equation, and things that let you make money go in the profit equation, hence cost and profit. Okay? So I need to make a cost equation. What cost me money here? The material costs me $5.50. I'll put that one in red because cost usually is like red. So the material cost me $5.50. What else cost me money? The advertising cost me money. $1,400 in advertising. That costs money, okay? So I need to write a cost equation. Notice that my variables kind of match up with a cost equation. The Y is the amount of money, okay? And X is the amount of hats. So my cost is going to be Y, the amount of money that it cost me to get started equals, well, each hat costs $5.50. Each hat costs $5.50 to make, right? So how could I write that? $5.50x. That's right. $5.50 per hat, or each hat, or for every hat. Those words always give away the variable. But we also have this advertising thing that we had to spend money on. So how am I going to include that in my equation? Yes, plus 1,400. So what this equation is telling me is I spent $1,400 here right out the gate to advertise for my hats because they're awesome. And then every hat that I made cost me $5.50. If I add all that together, I get the total amount of money that I had to spend on this whole project for my hats. Okay? Now, hopefully I'm going to start selling hats, right? People are going to buy them because they're pretty sweet. So now I'm going to make what we call a profit equation. This is the money that's coming in now. So I'm going to write Y equals again because I'm talking about money. The amount of money that I get from selling hats is equal to what? $12.50. So 12.5 times X, the number of hats that I sold. Is there any other way I'm making money here? No, people aren't giving me donations or anything, so that's it. All right? These are my two equations, a cost equation and a profit equation. I probably should have changed this color to green because then I'd be making money here, but you get the idea. All right? Now, this is a system of two equations. What can I do? I could graph them. They're both in slope-intercept form. Is graphing going to give me necessarily an exact answer? No. So it doesn't say show a graph. It doesn't say make a visual thing of it, so I'm not going to bother with making a graph. So we're down to substitution or elimination. Substitution seems like the better option here. How come? Yeah, we have the variable already solved. Actually, we know what y is in both equations. So this is a really easy substitution problem now, okay? So let me change colors back here. This equation right here tells me that y is 12.5x, which means I can take y, which is 12.5x, and substitute it in for that y right there. Because when these two lines cross, we'll break even, right? This line is going to look kind of like this. My cost equation looks kind of like that. My profit equation looks kind of like that. Up until this point right here, I'm losing money. But as soon as I get to here and this profit line crosses over the cost line, now I make money for every hat that I sell, which is good. That's what I want. So I got to find that point right there. And at that point, the y values are exactly the same. And so are the x values. So I can take this y right here, which is 12.5, and substitute it right there for that y. So I can write my equation. 12.5x equals 5.5x plus 1,400. Okay, just solve for x. What do we do? Yeah, I'd probably subtract the 5.5x. Just like always, we want to get all the x's on one side and all the numbers on the other side. So what's 12.5 minus 5.5? 7. Is that it? X, good. Equals 1,400. All right, solving for x, what do we do? Divide both sides by 7, and we got x equals 200. What? 200 hats. Remember, x is the number of hats sold. Really nice that we wrote that down, because now we remember that we're not talking about dollars here. We're talking about hats. And the problem asked me, for how many hats do I have to sell to break even? Well, the answer is what? 200. I got my answer already. I'm done. But if it asked me to find out how much money I would have made at that point, how much money would I have made? Think about it. If I'm breaking even, then how much money have I made on this project? 0. It's interesting because the graphs of these two lines would not cross at 0, because if I take 200 and plug it into either one of these equations, I don't get 0. But I've made as much as I've spent at that point, which means in total I have made nothing. But from that point on, I start making money. Okay? How much money have I brought in from the sale of hats? That would mean take the 200 and plug it into 12.5x times 200, and then you could get your answer. But if they just say how much profit do I have when I break even, you got nothing. You haven't spent anything, you haven't sold, you haven't made anything at that point. But after that, you've started to make money. A puzzle expert wrote a new Sudoku puzzle book. His initial costs are $864. Finding and packaging each book costs $80. The price of the book is $2. Is that $80 or 80 cents? 80 cents. Wow, that's kind of a big difference, huh? Okay. All right, so if that's 80 cents, that should say, right here, I'm going to change that to $0.80 so that I can tell that that's 80 cents. The price of the book is $2. How many copies must be sold to break even? So, what kind of problem are we working with here? Well, it's a story problem, but what kind of story problem? It's a break-even problem. See how it says break-even right here? As soon as I see that break-even problem, I know that I have to make two types of equations. What types of equations do I have to make? A cost equation and a profit equation. So I need to define some variables first. What are my variables going to be? I can use X and Y, but I want to say what they are. Equals number of, yeah, we're talking about books. It says how many copies must be sold. So number of books, and then amount of money, yep. Okay, and we're going to use X and Y again. And which one's X? The amount of books is X. And the money is always going to be Y. So that way in these equations I can write Y equals the amount of money equals stuff. Okay, now we need to come up with a couple equations. Which one do you want to do first? It doesn't matter, so just pick one. What? Well, it's either cost or profit. Okay, profit. So that means we're looking for stuff in the story problem that is doing what? Making money. That's right. So amount of money equals the thing that's making me money is the cost of the book. The price of the book is $2. $2 per book. So Y equals 2X. That's right. Is there anything else here that's making me money? No, that's it. Okay, so now we switch to cost. What are we going to have for cost? Y equals, again, because we're talking about money. The amount of money that I spent is, we got 80 cents X. 80 cents, 0.80X, so it's 80 cents per book. Any other costs here? Yeah, we also spent, it said initial costs are 864. We weren't even creative enough to say what those initial costs were in this problem. That's okay. So I write 80 cents X plus 864. Okay, what happens now? Yeah, we have a system of equations here, and we want to use substitution in this case because we already have an equation solved for Y here. And this one is too. So we know what Y is. Y is 2X, which means I can take that 2X and substitute it right there for that Y, which makes me write 2X equals 0.80X plus 864. And then just like in the last problem, we're going to solve for X. So what do we do? 0.80X from both sides. All right, and we get 1.2X equals 864. And now what? Divide both sides by 1.2. I can barely squeeze that in here. But we get X equals what? What was it? 720 books. And there's your answer. All right, there's two more problems in this section. We have a local zoo filling 2 water tanks for the elephant exhibit. One water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons per hour. The second water tank contains 29 gallons of water and is filled at a constant rate of 3 gallons per hour. When will the two tanks have the same amount of water? What are we dealing with here? What? Rates. Yeah, okay, so they're giving us a rate of change. What is a rate of change in Algebra 1? In an equation. It's what? Yeah, it's the slope. So if I write these equations in slope-intercept form, they've given me the slope here. That's my rate of change. And they've given me the slope here. That's my rate of change. So in this problem, what am I dealing with? Like, what's the problem asking me to do? When what has the same amount of water? The two tanks. There are two tanks in this problem. Tank 1 and tank 2. Are those my variables? No, they're not. They're my equations. We have two tanks. One starts off with 50 gallons of water and is filled at a constant rate of 10 gallons per hour. The other has an initial quantity and is being filled at a constant rate. In the last two problems, we had cost and profit equations. In this one, we're dealing with two separate objects, and we want to know when they are going to have the same amount of something in them. In that case, your first equation is going to be the first object, and your second equation is going to be the second object. So now that we know that, we have to come up with two variables. They're not the tanks. What are they? The amount of water in the tank. And what's the other? Time. Because they're telling me a constant rate of 3 gallons per hour. Hours are changing. So this is time. Now that we know the two things that are changing here, and we know that our two equations are going to be equation 1, tank 1, equation 2, tank 2, what are my two variables? X and Y, that's fine. A lot of times people will pick T for time and W for water, and that's fine too. Both of those variables make sense. But we can go with X and Y. And now we need an equation for tank 1. Y equals the amount of water in tank 1 equals 10x. The constant rate 10x, 10 gallons times the amount of hours that have gone by, plus the 50 gallons that it started off with in the beginning of the problem. And now we have tank 2. The amount of water in tank 2 equals 3 gallons per hour, so 3x, plus 29 gallons. All right, now what do? These two equations are correct. What happens now? Substitution, sure. We want to solve the system of equations. We want to know when the two tanks will have the same amount of water. Okay? So to do that, we have to say that this amount of water will be the same as this amount of water, which means I can take this and substitute in what this is for that y right there. And if I do that, I have 10x plus 50 equals 3x plus 29. Now what? We're solving for x, so we're going to subtract 3x from both sides. And we get 7x plus 50 equals 29. Now what? Okay, subtract the 50. And we get 7x equals, what is that? (29 minus 50). Yeah, negative 21. Okay, and we're solving for x. Divide both sides by 7. And we get x equals negative 3. Negative 3 what? That's time. And our units are hours. So actually over here we probably should have wrote hours. Okay, so in negative 3 hours, the water tanks will have the same amount of water in them. So is that my answer? No? Why not? You can't have negative time. That's right. So when will the two tanks have the same amount of water? Explain. Your answer here is not negative 3 because we can't have a negative time. So therefore, will the tanks ever have the same amount of water in them? No. So your answer has to be, they won't. And you have to say why. And you could say, can't have negative time. So that all needs to be your answer. There's lots of ways you could say that, but that needs to be your answer. And actually, if you take a look at tank 1 starts off with 50 gallons in it already, and it's getting lots of water, 10 gallons per hour. Tank 2 starts off with less water, and it's not even filling as fast as this one is. So it's less water and it's filling slower, which means this one's never going to catch up to this one. So that makes sense. And actually, once you set up those two equations, you could probably have saved yourself doing that if you thought about it and realized there's no way that's ever going to work. Okay? This is the appropriate answer here.